Good afternoon, everybody. Welcome to another sunny, exciting afternoon of Chem 1105 with your host, me, Dr. White. Boy, it's nice out there. I was out earlier. It's a nice summer day, other than the smoke, which wasn't too bad. All right. Well, I've got a lot to do, so I better get going. All right. First of all, let me make sure you can see it. You can. This Thursday, I will be giving test number 3 online, just like 1 and 2. You'll be able to download a password protected PDF file for test number 3 in the assignment area Blackboard. Around 8 a.m. or maybe even a little earlier, I will send out a password that will allow you to open up the password protected PDF file for test 3. You'll have until Friday, 4 p.m. to finish test 3 and upload test number 3 as a single PDF file to the assignment area of Blackboard. Should take you about 45 minutes to do the test. I've given these kind of tests face to face, so I know how long it will take. Under 50 minutes, most people. But if you need up to 3 hours, if you don't tell, I won't. I said it was silly Tuesday. Boy, it's getting silly. All right, an important note. Test number 3 will cover chapter 6 and chapter 5, part 2. This is gases and solutions. It has 20 problems, 9 pages, 5 multiple choice. Some of the questions are multiple part. Gases is 48 points on that test. Solutions 57. It adds up to 105. So there's 5 bonus points. And you'll need a scientific calculator. If you don't know how to use that, come to my office hour or email me and I'll set up a Zoom meeting to help you out. By next Sunday, I'll have the grades that are earlier in Blackboard. I'll send out an email when it's posted. I'll also, by next Sunday or earlier, send out individual emails each of you will get with each points you got for each answer on test 3. Next Monday, I'll go over test 3 in our Zoom meeting. I'll cut it out. I like those special effects. Well, it is silly Tuesday. But I'll have it in a separate video that I'll send you to ULR for that video. And today, later on, I will be doing, guess what? The review for test number 3. And tomorrow, I will be doing chapter 5, part 2 problem set. And I'll do some more problems on molarity today. Give me 1 second. Actually, it was more than 1 second. I had to fix something up. But anyways, I'm back. All right, so that's test number 3. Another thing I put out this morning that you should be aware of in Blackboard, I posted test number 2 answers that I did yesterday in a private video. And here's the link. If you click on it, oh, who's that handsome guy? And we go like this. You'll see I'm going through the key. But anyways, that's test number 2 answers. That's in that link in the announcement. And you should also have gotten an email from Blackboard. All right. Before I move on, any questions about test number 3? Going once, going twice. I went to a lot of auctions in my life. Done. All right. Let's do today. I'm going to do the lab, and then I'll do my review for test number 3. And then we'll do some molarity practice problems. I think you could use them and they'll help you, which is a good thing. And then we'll go through new material. That'll be on test number 4. Oh, I gotta get this finger fixed. Stay up there. All right. Today's lab is called Engineering a Better Airbag. And the airbag they're talking about, let's see if I can find one on the internet. And you can see here, those are airbags. Let's see if we can get actually images. And you can see these are deployed. Thank goodness I've never had that. I hope I never do. The only accident I was in, someone rear-ended me and it wasn't super fast and a policeman saw the whole thing. But anyways, these are airbags. And when there's a collision, they inflate to protect people from colliding with things of hard surfaces like the steering wheel in your car and protect you. Now, how does an airbag work? And here's today's lab. Let me remind you, you'll be working with not dangerous chemicals, but anytime you anything with chemicals, wear your safety goggles, wear gloves. You'd like to wear an apron, you can. Also, I'd highly recommend, since you're working with vinegar, work in an aluminum tray. I'm not sure vinegar attacks marble, but I hate to have you find out it does. If you notice, they have time requirements. So considering if we were face-to-face doing this lab, we'd do it in about an hour and a half or so. But here, 30, 40, 50 minutes. So you can do it quicker. All right, now let's talk about the background. Now, when you fill that bag up to protect yourself, gas is being used to fill that up. Inflate it, just like you blow air into a balloon to inflate it, the same thing happens. And as I've taught you, one of the most important things in gases in chemistry is the ideal gas law, PV equal nRT. Let me make this a little larger. Is that better? And P is pressure, but it's in atmospheres. V is volume in liters. N is the number of moles. R is the universal gas law constant. Oh, look, that's the one we use all the time. 0.0821 liter atmospheres per mole K. And T is temperature, but that has to be in Kelvin. Now, in an automobile, when you're in an accident, it senses at a certain speed. If it happens, what happens is a pellet of sodium azide, NaN3, explodes. Explosion is a way of saying gives off gas very quickly and sometimes very violently. And the reaction is there's a catalyst, and I forgot what catalyzes. It could be a heat or something. And the sodium azide, which is the S is solid, forms sodium metal and the nitrogen gas. And that nitrogen gas is what inflates the airbag. Now, you're forming sodium. Sodium metal is very dangerous stuff. It reacts with water violently to give off hydrogen gas, which is also dangerous. And water only makes it do that quicker. So they put in ferric oxide, which reacts with the sodium metal to form sodium oxide and iron, which is pretty harmless. All right, unfortunately, sodium azide is toxic. So if we go to some dump yard where they have junk cars and they're all got steering wheels and other things with uninflated airbags, there's a lot of sodium azide in those junkyards, in the junk cars. And that's a hazard to our environment. We've got enough problems now. Now, in this lab, you're going to be investigating the reaction of sodium bicarbonate, baking powder or baking soda, and vinegar. And I've never understood why they call that white vinegar, other than it's clear as opposed to colored vinegars, but it's called that. All right, here's the equipment you need. You've already used all this. Remember, you should always wear protective clothing. You should not eat, drink, or chew gum while doing these activities. Wash your hands before and after, even with gloves on. All right, now, let's talk about the reaction. And I'm going to go to my whiteboard. And acetic acid, 2 carbons, 4 hydrogens, and 2 oxygens is called a carboxylic acid. It's organic chemistry. Now you're on my home field. And when you dissolve it in water, we call that vinegar. Now, sodium bicarbonate is baking powder and also baking soda. And when you react it, you'll learn next chapter, it's an acid-base reaction. Here's the acidic proton, here's the acid, here's the base, and it reacts to give this salt called sodium acetate plus water plus carbon dioxide, and the arrow up tells you this is a gas. And that's what you're going to be doing. You're going to be reacting this vinegar, which is really the acetic acid, with baking soda, which is really the sodium bicarbonate. And the main thing you're going to be making is the gas carbon dioxide. Now here they show you an intermediate. This is called carbonic acid. It immediately decomposes to water and CO2. By the way, S is solid, AQ, you know, is aqueous. And here, L liquid, G is gas. Now, you're going to be using these, I don't have one right at hand, the 6 by 9 inch plastic Ziploc baggies they give you. The volume of that bag is 1.2 liters. Now, you're going to have to find out wherever you are, what is the atmospheric pressure? And how do you do that? Oops. Now you can see it. I like to go to my favorite Weather Underground website. And the Weather Underground, and if we put in Glen Ellen, oh wait, what's the zip code? 60137. Wherever you live, put in your zip code. You'll see the temperature, and if you scroll down, you'll see where it says here pressure, 29.95 IN, that means inches of mercury. And you're going to have to convert that to atmospheres. And I'll show you how in a little while. But if you don't have a barometer in your house, just go to Weather Underground. If you want to use weather.com, I'm not going to stop you, but I like Weather Underground better. And it's at weatherunderground.com, which is wunderground.com. If not, hold on, let's go to your favorite search engine. Google is mine. And put in Weather Underground, and it'll take you right to that website. You could even put in your city, if I can spell it, and it'll take you right there. You don't see where I got to Glen Ellen. Now, again, scroll down, and you'll need the pressure in inches. You're going to have to convert that, and I'll show you how in a little while. All right, now here they show you how, and I'll show you in a little. Now, you have a thermometer, it's in degrees C, and you convert to Kelvin by adding degrees C plus 273. Now, the ideal gas law, PV equal nRT, if you solve for N is the number of moles, and that will be the number of moles of carbon dioxide you'll need. And you have the pressure, but you've converted to atmosphere. The volume, and I'll show you this in a second, is 1.2 liters. R is 0.0821. And temperature is degrees C plus 273. Relax, I got a special gift for you today. Remember, this is chemistry. I'm a chemist. All right. Now, if you look at the reaction, and let's look at mine. This is a balanced chemical equation. And for every 1 mole of CO2 produced, you need to react 1 mole of the vinegar, acetic acid in the vinegar, and 1 mole of the sodium bicarbonate. So if you find out how many moles of CO2 does it take to inflate a 1.2 liter bag, you can then determine how many moles of acetic acid and how many moles of sodium bicarbonate you need to weigh out to do that. I've kept you in suspense, so now let me do one thing in Blackboard. Go to student view. We're in student view because when I'm in my view, I can do things you can't. It is silly Tuesday. Now, if we click on assignments, oh, I forgot to talk about something. I'll do it right after the airbag. You'll see lab 11, engineering a better airbag. And if you scroll down, you'll see the actual PDF for the lab, the instructions, next cam scanner, then the, engineering a better airbag, Dr. White's help sheet. Oh my goodness, shh, don't tell me I'm being nice. Shh, remember, mum's the word. And if you open that up, I have it both as a PDF file, and you'll see this, my help sheet. Now, here it shows PV equal nRT if I solve for N. By the way, these 3 dots in a triangle is math for therefore. Therefore, N equal PV over RT. Now, for the temperature, you'll need it in Kelvin, and you'll take degrees C plus 273. That will be your temperature you'll use. Next, pressure has to be in atmospheres. But if you saw the one we had was, what was that, 29.5 inches of mercury or 29, whatever. You'll take that, multiply it by 25.4, then divide by 760, and that will give you your pressure in atmospheres. Now here, N, now that N is the number of moles you calculated. How do you do that? To fill a 1.2 liter bag. So you're going to use PV equal nRT. V is going to be 1.2 liters. P you get from here. T you get the thermometer, get degrees C in that. And V, like I said, is 1.2 liters. And you're going to get a number, N. Now, the reaction you're using is this one. For every 1 mole of acetic acid, 1 mole of sodium bicarbonate, you make 1 mole of CO2. Note, you'll need the number of moles of acetic acid, number of moles of sodium bicarbonate to generate N moles of CO2. Remember, N moles of CO2 is calculated using this equation right here. And here's V. P you get from the weather underground, then you convert to atmospheres. Temperature you'll get from your thermometer, and you'll add 273 to get temperature. Put those in there, you'll get N. Now, your vinegar is a solution. And I haven't done this to this extent, but well, actually, we've done something similar like that. But to determine the milliliters of vinegar you need, you do the following calculation. N moles of acetic acid. And that's the N you calculate right here. Times 1,000 divided by 0.833. That's the molarity, moles per 1,000 milliliters, except you turn it upside down for this, will give you how many milliliters of vinegar. Now, for every 1 mole of CO2, you need 1 mole of sodium bicarbonate, going from, and that's equals N moles of sodium bicarbonate. Use the same N you calculated up here. You multiply it times its molecular weight per mole. Now, for the same activity 2, you'll do the same calculation right here, except N is going to change. The volume will be different for activity 2 and activity 3. You don't have to do anything there except calculations. I'll come back to that. Let's take a look at the lab. So I've gone through these calculations. For the first experiment, you need to find room temperature in atmospheres, look up weather underground, convert it. You need the room temperature in Kelvin. Moles of CO2, I've given you the balanced chemical equation. Grams of sodium bicarbonate, you either go back to my help sheet, and the volume of acetic acid or vinegar needed. Here's what you're going to do. You'll weigh out the sodium bicarbonate needed here. That's where volume is 1.2 liters. In the graduated cylinder, you'll measure out the volume of acetic acid. Again, go to my help sheet. Now, in the bag, the Ziploc bag, what you'll do is hold it over the edge of I don't have one up here, of a container, your beaker. So the bottom forms 2 V's on it, or like a W, 2 compartments. Carefully put the solid in one side, and it'll be on this lip of the beaker, so there'll be a barrier. Carefully put the vinegar on the other. Zip it closed, still keep it on the edge of the beaker so there are 2 U's, and then squeeze out all the air and close it finally. Once it's closed, what you'll do, mix everything together, put it down on a tray or something. Hopefully you sealed it tightly. Make sure before you mix it, it's sealed tightly, and then watch it fill up with gas. And you might want to shake it a little until it's all clear and it's reacted. Now, you're going to do it a second time by adding the original run. You'll add an additional 0.3 of a gram of sodium bicarbonate and an additional 5 milliliters of the vinegar. You'll put it in like this on the lip, one side the sodium bicarbonate, the other the vinegar. This is in a separate second bag. You'll seal it almost, get the air out, close it totally, shake it, and watch it fill. And you can compare how much it inflates the first and second bags. And then you'll do it a third time. And now you'll use an additional 0.5 over the original amount of the sodium bicarbonate and an additional 10 milliliters over the first run of the vinegar. So if you use, I'm just picking a number out here, 5 milliliters in your first run. For the second one, you'll use 10 milliliters of vinegar in this activity right here. And the third one, you will use, you started with 5, then you'll add 15. So you're adding each time 5 and then 10 milliliters to the original amount. Now you'll have 3 bags and look at those and decide which one's the most filled or inflated. Now, in an activity 3, you'll assume the airbag for a car is 80 liters. That's your volume. You'll go back to N equals PV over RT and calculate that for the temperature, pressure, now the volume of 80, how much CO2 is, and then you can calculate how much grams of sodium bicarbonate and milliliters of vinegar. Then you'll do that calculation a second time, except use a volume of 160 liters. So if we look at the table, in table 2, how many grams of vinegar and everything, and your observation was all full, sort of half full, really full, things like that. Now, in table 3, you'll do the same calculations. I'll go back in a minute to the help sheet, but use, instead of 1.2 liters you did for your own little bags, you'll assume you're doing it for a full car bag, airbag, and you'll use 80 liters for the volume and calculate. And you don't have to rewrite the balanced chemical equation every time. Calculate the grams of sodium bicarbonate and the volume of vinegar. And for the third activity, this table 4, you'll now use a volume of 160 liters. And you'll calculate, again, you don't have to rewrite the balanced chemical equation. You did it already earlier. And you'll calculate the mass of that and the mass of the vinegar. Now, the plastic bags, after you empty it, and I'd rinse it once, you can dump in the garbage. All the liquids can be left over, from anything in the bags. You can dump down the sink and let your sink run for a couple of minutes, cold water, after you dump all 3 down there. All right, let's go back to my help sheet. All right, what you're going to do is use this equation, N over PV over RT, to calculate the moles of CO2. Here's the temperature, you'll measure that. The pressure, you get inches from the weather underground. And you'll calculate for V equal 1.2 liters, what N is. You'll put N in here to calculate milliliters of vinegar, put N in here to calculate grams of sodium bicarbonate, baking powder, or soda. I always say the wrong one. All right, and calculate in activity 2, you'll use this, except I don't have it here. You'll use V equal 80 liters. Let's call it 80.0, 3 significant figures. Oh, wait. Nope. These are the calculations. In activity 3, you'll do for activity 1, you'll calculate these, except use V as 80, and later on V as 160.0. This is a busy lab. It's fun though. Now, if we look at the write-up, here's from your table 1, put the data in. Here's the grams, what you did for each trial. Remember in 2, you had, I think, 0.3 and 5 milliliters, then 0.5 and 10 milliliters, and how full was your bag. And then for table 3, you do the calculation that I showed you in my help sheet for 80 liter instead of 1.2 liter. And for table 4, you'll use 160 volume instead of 1.2 liters. And you'll do the same calculation. And you answer this question. And essentially they're asking, is this a good replacement for sodium azide? Now, one thing I'll help you answering that question, when I started in the chemical industry long ago, I was very lucky I had a mentor. One of the nicest, smartest people I've ever met in my life. Unfortunately, he's passed long ago. And that was Sid Shapiro. When I started, I was in my late 20s, 25, 26, maybe a little older. When I started at this company, I was a postdoctoral fellow at UIC, or Chicago, University of Illinois, Chicago Circle. But then I got into industry. And when I was in my 20s, Sid was already in his mid 70s, but he had been with that company for a long time. It was a great chemical engineer, and he knew as much as any PhD chemist I've ever met. And he was my mentor. And one of the things he used to teach me, and actually bang into my head, not physically, but mentally, was common sense is not common. So if I tell you to answer question 1 using common sense, it's not common. And I've solved some really hard problems by using common sense when other people didn't. It was amazing. The education, practical education Sid gave me. Thank God I had it. All right. Any questions on lab today? If you do have questions, always feel free to email me. Also, always feel free to come to my office hours. If you can't come to my office hours, always feel free to email me and see if I can set up a Zoom meeting with you. That's the one nice thing about Zoom. If we're at COD face-to-face, if I'm not at COD, well, you're out of luck. But with Zoom, we can set up a meeting easily, because I don't have to, and you don't have to go to College of DuPage main campus. All right. Let me close this. Don't need this. And let me open this. And if you go to the lecture section of Blackboard, you'll see I have cleverly hidden a file called Chem 1105 test number 3 review. And what you see on the screen is in that file that you can download. And these are things you should know for test number 3. We've already practiced most of this. All right, first of all, when it comes to pressure, and there's a mistake here, that should be mm. 760 millimeters of mercury, well, I have that, it should be torr. I'll have to go back and replace this. All right, 760 torr equals 760 millimeters of mercury. That's what mmHg equals 1 atmosphere. And you should know how to use your good buddy, your good friend, how to convert from one to the other. We did that in problem set for chapter 6. Next, in case you forgot, if you need temperature in Kelvin, it's degrees C plus 273. Now, I talked about Boyle's law. Boyle's law deals with this pressure and volume. Nothing else changes, those two. And Boyle's law is P1 times V1 equals P2 times V2. Good news. And let me open that one up too. If you go to the lecture folder and you look up the file important information, test number 3, you'll see I got it right here. All the information that you don't have to memorize, but you do know how to use. And Boyle's law is there. Let's go back to the review. Boyle's law is P1 times V1 equal P2 times V2. P1, initial pressure, where you start. Volume, V1, initial volume, where you start. I look like I'm a football referee. Touchdown, no. It is Silly Tuesday. But anyways, P2, final pressure, where you end up, and V2, final volume, where you end up. And you'll be given P1, V1, and either P2 or V2. And you'll have to solve for the other. And remember, when you want to get rid of something on a side for multiplication, you divide by that. Next, the ideal gas law, PV equal nRT. P is pressure in atmospheres, and you have to convert that. You go back and look at chapter 6, practice problem answers, you see I show you how to do that. Remember, this was the one that was 15 points. And V is volume in liters, which I'll always give you in liters, you'll calculate it. N is number of moles, but you got to go from grams to moles. We've done that. T is temperature in Kelvin. Use this formula to go from degrees C to Kelvin. And R is the universal gas law constant given right here. By the way, R is 3 significant figures. And don't forget, your car tires have gas in them. And in the winter, if your car's parked outside, temperature gets real cold. So the gas in your car tire gets real cold. And PV equal nRT tells us that when the temperature goes down and your car tires V, N, and R don't change, therefore the pressure will go down. And also in the summer, we've been lucky this area. I better shut my mouth so I don't jinx us. But so sad, those people like in Phoenix where it's like 120 Fahrenheit. And we're not talking about heat index. We're talking actually thermometer heat. But in the summer, the temperature goes way up. And PV equal nRT tells you you should check your car tires. Why? Well, in your car tires, V, N, and R are constant, but if the temperature, wrong way, the temperature goes up, then the pressure will go up. All right, well, I have my whiteboard here. We learned about in gas, by the way, this is a symbol I used when I was taking notes, something new, end of whatever the idea I was talking about. We talked about boiling points. Which is boiling temperature of liquids. And you should know that when the vapor pressure of a liquid equals atmospheric pressure, that temperature is the boiling point. I could never spell atmospheric right. This should be an H. But anyways, the higher the altitude, the lower the atmospheric pressure. That means you need a lower vapor pressure. That means you have a lower boiling point. So if you go up to the Himalayas, the boiling point of water will be a lot lower than it is here in Chicago, because you're a higher altitude, lower atmospheric pressure. And this is something you should know. So higher altitude, less atmospheric pressure, lower boiling point. Next, I talked about Dalton's law of partial pressure. The total pressure of a mixture of gases is the sum of the partial pressures. Oh, I didn't know I had it here. But boiling point of a liquid. Hey, I spelled atmospheric right. All right. But anyways, boiling point of a liquid is when the vapor pressure of a liquid equals atmospheric pressure. The higher the altitude on the Earth, the lower the atmospheric pressure and the lower the boiling point is. Now, next, solutions. Remember, when we talk about a solution, which is a mixture of two or more compounds or chemicals or stuff, doesn't sound scientific. But anyways, the solvent is the component of the solution present in the greatest amount, and the solute are the other component or components. Now, I talked about something that at first glance you think is a solution, but it's not. And that's a colloidal dispersion. And a colloidal dispersion, you know, scatters light. Remember my fancy flashlights. But a solution will let light through. A colloidal dispersion will cause it to go and won't let light through. Now, examples of that I don't have here, but I can write down. You should know. Examples of colloidal dispersions: milk, latex paint, your blood, but don't try and put your flashlight through your blood. Please don't cut yourself. All right. And also mayonnaise, ketchup, mustard. They're all colloidal dispersions. All right, next I talked about an important concept, like dissolves like. And that means polar solutes are soluble in polar solvents, and nonpolar solutes are soluble in nonpolar solvents. What are polar things? Water, salts like sodium chloride, and alcohol, or alcohols like rubbing alcohol and others. All right, what are nonpolar? And that would be vegetable oil, gasoline, baby oil, Vaseline, and those are examples of nonpolar. All right, things you should know. The solubility of a solute is the maximum amount of solute that will be dissolved in a given amount of solute. You can't put one more molecule because it will precipitate, form a solid at the bottom of a test tube. And saturated, it means you've reached the solubility limit. And that's the maximum amount of solute that can dissolve under the conditions at which the solution exists. Next, we have a dilute solution. And a dilute solution is a solution that contains a small amount of solute relative to that you could dissolve. Concentrated solution is a solution that contains a large amount of solute relative to the amount that could be dissolved. And really important one, aqueous solution, which is shown by A, bracket A, Q, close bracket. And an aqueous solution indicated by bracket AQ, close bracket, the water is the solution in which water is the solvent. Aqueous solution, water is the solvent. Speaking about water, I just had some. Now, talking about different ways of determining the amount of solute in a solution, we call that concentration. The only one I asked you to learn about is molarity. And molarity, which is shown by capital M of a solution, I will never ask you what's the definition of molarity in words, is a ratio number of moles per liter, but molarity, moles of solute per 1 liter of solution. But since 1 liter is 1,000 milliliters, we use moles of solute per 1,000 milliliters of solution. Now, from the last test, there are things you got to know how to go from moles of a compound to grams of a compound. And 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of a compound is the sum of all atomic weights. And if I look at the clock, oh no, it's time for a break. So you're going to have to wait and come back to see the rest of the review. Time for a 5-minute break. I'll see you in about 5 or 6 minutes. I'm going to get up and stretch. And let's get back and finish our review for test number 3 coming up this Thursday. All right. If we look, we have molarity equals moles of solute per 1,000 milliliters solution. And I'm going to go through another practice problem today. And tomorrow I'll go through the whole solutions chapter 5, part 2 practice problem. And remember, I showed you yesterday, and I'll do one in a little while, this 2-step molarity problem. That's in step 1. You convert milliliters you're given to moles of solute. Then you convert moles of solute to grams of solute. And that's the important thing. 10 points. Oops. All right. That's the review for test number 3. And I thought, how can I help you? And as you figured out by now in my class, repetition is good for your grade, which makes me happy when people do good. So let's look at a few things we should practice. And I'll do one, then I'm going to let you have fun too. I'm going to share the fun today. What does 1.73 capital M mean? Capital M, as soon as you see that between a number and a chemical formula, capital M means molarity, which is moles solute for this class 1,000 milliliters. And therefore, what does this mean? 1.73 moles of hydrochloric acid, HCl, per 1,000 milliliters. I'm going to let you have one. What does 8.667 capital M NaCl mean? Your turn. And it looks like everybody's done. And let's see if you're right. Capital M means molarity, moles of solute per 1,000 milliliters. And what does this mean? 8.667 moles sodium chloride, NaCl, per 1,000 milliliters. Oh, let's do one more. And I'll let you try this all on yourself. What does 3.461 capital M KOH bracket AQ close bracket mean? And what is the solvent of that solution? Your turn. Oop, wrong thing. Hold on. Right thing. Again, what does that mean and what's the solvent of that solution? All right, it's time to proceed. Capital M, molarity, moles of solute per 1,000 milliliters. And therefore, this is 3.461 moles of KOH, potassium hydroxide, per 1,000 milliliters. And the bracket AQ closed bracket, aqua or aqueous, means the solvent is water. All right, let's look at this. Could be anywhere from 6 to 8 points. How many moles H2SO4, that's called sulfuric acid, are 126 milliliters, ml is milliliters, of a 2.23 capital M H2SO4 solution. All right, let's do this stepwise. Right here, what are you being asked to find? What are you given? All right, what are you being asked to find? Moles of H2SO4. What are you given? There's 126 milliliters of solution and this thing. And what does this mean? Oh, look, capital M in between a number and chemical formula, molarity. That means 2.23 moles of sulfuric acid per 1,000 milliliters. That's ml, sorry about that. Now, the only number we really have to start with is 126 milliliters. There's a conversion factor. Your turn. What units do I want my answer to be? Oops, wrong thing. Right thing. I'm asking what units do I want my answer to be? And the answer is right up here, moles of H2SO4. Now, it's time for you to use your good buddy, your good friend, unit analysis. What units and numbers go on top and bottom of that ratio? Oh, you people are fast today. Good. So it's time to use your good buddy, your good friend, unit analysis. Whatever we're trying to get to, the units go on top of the ratio. Wherever we're trying to get rid of, the units go underneath. And I'll write those. Moles of sulfuric acid, H2SO4, milliliters. And where do we get this number? Hold on. One of these days, I'll remember, use print, don't use cursive. All right. How do we get those numbers? From knowing the molarity here really means this right here. And that's 2.23 moles of sulfuric acid per 1,000 milliliters. Notice milliliters divided by milliliters cancel out because anything divided by anything divided by itself equals the number 1, cancels out. We're left with moles of sodium of sulfuric acid, H2SO4. I can happily pick up my calculator, turn it on, clear it. 126 times 2.23 divided by 1,000. And my calculator gives me this number. And I know when we're doing multiplication division, you get the same number of significant figures in your answer as the numbers you're multiplying and dividing. It has the fewest significant figures. All non-zero numbers are significant. 3 there, 3 there. The 1,000 is part of the definition. Exact number plays no role. So this should have 3 significant figures. Keep the 2, keep the 8, keep the 0. Use the 9 to round off. Is that 4 or less, 5 or higher? 5 or higher, drop that. Increase that by 1. And the correct answer is that. And that's how you do it. All right, let's move on because we got a lot to do today. And the question is, how many grams of NaOH, that's sodium hydroxide, are needed to make 245 milliliters of a 1.121 capital M NaOH solution? All right, I'm going to do this one because there's other things I got to do, and we'll go through some of these tomorrow again. What are we trying to find? Grams of sodium hydroxide. By the way, if you want to do this yourself, back up the video, press pause, and figure out what are you being asked to find? What are you given? You're given 245 milliliters. Oops, did it again. $245 milliliters. And you're given the molarity of the solution. Oh, I gave it away. And as soon as you see capital M, what does that mean, molarity? What it really means is there's 1.121 moles sodium hydroxide, NaOH, per 1,000 milliliters. All right, now, there's no way you can go from milliliters to grams in one step. There's no way you can go from milliliters to grams in one step. Therefore, you need 2 steps. Whenever you're going from milliliters to grams, you need 2 steps. And if you look at important information, test number 3, you'll see molarity 2-step problems. Step 1, milliliters to moles. Step 2, moles to grams. In case you forgot, 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of the compound is the sum of all atomic weights. So now we need to do the 2 steps. So we need to go from mils, hold on. I keep on using cursive for milliliters to moles. So this is step 1. And what do we have? We have 245 milliliters. And we want to go to moles of what? Well, eventually we got to get to grams of sodium hydroxide. So we have to do moles of sodium hydroxide. And now we'll use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath the ratio. And now write that in. And where do I get these numbers? From the molarity, which means this right here. 1.121 moles of sodium hydroxide per 1,000 milliliters. Notice milliliters divided by milliliters cancel out because anything divided by itself equals the number 1, cancels out, and I'm left with moles of sodium hydroxide, which is what I want. So now I'll turn on my calculator, clear it from the last problem, 245 times 1.1, 1.121 divided by 1,000. And my calculator gives me this number. But it says on test number 3, please use proper significant figures for all calculated answers. 3 significant figures, 4 significant figures. Well, my answer should be 3 significant figures. You get the same number of significant figures to answer as the number with the lowest significant figures you're multiplying, dividing by. 1, 2, 3. Use the 6 to round off. Step 4 or less or 5 or higher. And time's up. Hopefully all pick 5 or higher. We'll drop these. Increase this by 1. And the correct answer for step 1 is 2.75 times 10 to the minus 1 moles of sodium hydroxide. Are we done? No, because we want to get grams of sodium hydroxide. So now we have to do step 2, which you learned for test number 2, and that's moles to grams. And how do we do that? Well, we just calculated we need 2.75 times 10 to the minus 1 mole of sodium hydroxide and we want to get to grams of sodium hydroxide. So it's time to use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And don't forget the equal sign, Dr. White. And I'll write grams of sodium hydroxide, moles of sodium hydroxide. And where do I get these numbers? Well, in case you forgot, you can go to important information, test number 3, 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight is the sum of all atomic weights. Well, for every 1 mole, that's the molecular weight in grams. Well, I've got to calculate the molecular weight of sodium hydroxide. That's the sum of all atomic weights, 1 sodium, 1 hydrogen, 1 oxygen. You look on the periodic table, 1 sodium, the 3 significant figures is 23.0, oxygen 16.0, hydrogen 1.01. We've done this before. And this adds up to 40.01. 1 past the decimal, 1 to the right of decimal, 2. By the way, this is a number 1 there. And you get the same number of significant figures to the right of the decimal as the number with the fewest significant figures to the right of the decimal. And in this case, that would be 1. Keep the 0, use the 1 to round off. Therefore, that's 40.0. Notice moles cancel out. Boy, this mole stuff is thirsty work. And now I'll pick up my calculator. 2.75 blue double E minus 1. Oops. Minus 1 times 40.0. And my calculator gives me this number. Well, hold on 1 second. Let me clear this and do it again. And I got this number. This is rare. And this is 3 significant figures. 3 significant figures, exact number. And this is only 2 significant figures. So how do I make it 3? Simple. Add a 0 at the end. And that's how you do it. And we'll go through more of these tomorrow. Now with that, it's time to go into a new chapter that will be on test number 4. I do have to get that finger, test number 4. So let's open up this new chapter. And the new chapter is chapter 7. And the title is Acids and Bases. What's an acid? What's a base? Before I start going into that, I should say, of all the stuff I'm going to teach you this semester, this chapter probably has the most useful stuff you will use the rest of your life. Again, this chapter will have the most useful stuff you will use the rest of your life. So what's an acid? What's a base? Well, it turns out that's a real hard question to answer. And the first one, take a try. By the way, click, switches off on this slide, is a chemist called Arrhenius. And he came up with, guess what? The Arrhenius acid-base theory. And an arenous acid is a hydrogen-containing compound that in water produces hydrogen ions, H+. Again, switch is totally off. You'll see why in a little while. And then there's arenous base, and that's a hydroxide-containing compound, hydroxide meaning OH, that in water produces hydroxide ions, OH. I'm not going to show examples. You'll see why. All right, switch is on. Now, under Arrhenius theory and another theory I'll teach you, here's some key acids you should know. See, it even says on the screen. Oh, that was okay, sorry. Hint, know this. Now, hydrochloric acid is HCl. And that's the acid in your stomach that breaks down food. One of the great miracles of life in my mind is I have and you have cells in our body that make hydrochloric acid. Now, the next acid is called sulfuric acid. You should know the formula H2SO4. In the United States, and I think the world, the chemical that's made the most pounds per year is sulfuric acid. It's used in many, many important things. Now, another key acid is nitric acid, HNO3. And nitric and sulfuric acid are used together in organic chemistry to make useful compounds. The last one is acetic acid. Now, I'm not going to ask you to learn the structure of acetic acid. Dr. White knows it. But you should know acetic acid in water is called vinegar. And this is roughly approximately 4% acetic acid. This you don't have to know. And approximately 96% water. If you look up at any bottle of vinegar you can buy, except I think a couple places now sell old vinegar, 5% acetic, but essentially it's 4%. And now public service from Dr. White. If you look on your screen, you have Marucan gourmet all natural rice vinegar. That's probably the best, one of the best vinegars out there is that rice wine vinegar. And the best brand that I like is Marucan. And now even you can buy it at Jewel. That's amazing. For many years, you have to go to an Asian store to get Marucan. Now Jewel sells it. And another favorite vinegar of mine, you can get many, is apple cider vinegar. And there are many brands. And I like both of those. And that's acetic acid, an acid in. Oh, somebody has both brands, both the apple cider and the Marucan rice wine vinegar. Someone's a cook. I am. My father loved to cook, and he taught me how to cook. When I was a child, men didn't cook, period. That was a woman's job. But my father liked it. And even a lot of my generation, a lot of men don't even know how to cook. Sad but true. All right, so you should know, if you see the formula HCl, you should know that's an acid. If you see the formula H2SO4, you should know that's an acid. If you see the formula HNO3, you should know that's an acid. I won't ask you to learn the formula for acetic acid. Now, some important bases you should know. And if we were face to face, this would be on the screen on the whiteboard next to the screen in the class. I'd be writing this hint, know this, and then to the screen, I'd have an arrow. I would go this way, not that way. But since it's all on the same screen, I don't have to draw the arrows. All right, when we talk about bases, and I'll teach you what a base is. Sodium hydroxide, the old name was lye, is NaOH. Potassium hydroxide, the old name was potash, because they first found this potassium hydroxide in the ashes under people's cooking pots, is KOH. Ammonia is NH3. And finally, sodium bicarbonate is NaHCO3. If I put down NaOH, is that an acid or base? You should know that's a base. If I put down KOH on test, 2 points, is that an acid or base? You should know that's a base. Also, ammonia, NH3 is a base. And finally, NaHCO3, sodium bicarbonate, baking powder, and baking soda is a base. Now, if we go back and look at the Brønsted-Lowry acid and base theory, notice it says something important. In water. The only time you can use this if you're dealing with a solution in water. It turns out in chemistry, a lot of times you're not in a solution of water. So if you're not in water, you can't use the Arrhenius theory, which meant someone came up with a better theory. And that were two chemists independently at the same time. So it's called the Brønsted-Lowry acid base theory. And the Arrhenius theory does not explain acids in non-aqueous solutions. Non-aqueous means no water. Hold on, I have to be subtle. Hint, know this. You should know. Click, switch is on full. What is a Brønsted-Lowry acid? It's any substance that can donate a proton. A proton is H plus to another substance. An easier way to remember it, what is a Brønsted-Lowry acid? It's a proton donor. If I'm a Brønsted-Lowry acid, here, take my proton. I'm an acid, a Brønsted-Lowry acid. So you should know a Brønsted-Lowry acid is a proton donor, and a proton is H plus. Well, if a Brønsted-Lowry acid, an acid is a proton donor, you take my proton. What's a Brønsted-Lowry base? Well, hold on while I get subtle again. Hint, know this. And what's a Brønsted-Lowry base? any substance that can accept a proton being H plus from another substance. A better way of remembering it is a Brønsted-Lowry base is a proton acceptor. If I'm a Brønsted-Lowry base, hey, give me your protons. Give me your come on, give it to me. Give me your proton. I want your proton because I'm a Brønsted-Lowry base. If I'm a Brønsted-Lowry acid, I'm a proton donor. Here, take my proton. I'm an acid. Remember, under the Brønsted-Lowry theory of acid and base, an acid is a proton donor and a base is a proton acceptor. And if we go back to these lists, hydrochloric acid, sulfuric, nitric acid, acetic acid are all proton donors. That's why they're called acids. Now, if we go to bases, sodium hydroxide, potassium hydroxide, ammonia, and sodium bicarbonate are all proton acceptors, Brønsted-Lowry bases. Now, one of the important things about the Brønsted-Lowry theory of acid base, what was an acid under the Arrhenius theory is also an acid in the Brønsted-Lowry acid base theory. What was a base in the Arrhenius theory is also a base in the Brønsted-Lowry acid base theory. And you should know, get the hint? An Brønsted-Lowry acid is a proton donor. Acid, proton donor. Here, I'm an acid, take my protons. Here, take it, because I'm a proton donor, an acid. If I'm a base, you should know. A Brønsted-Lowry base is a proton, remember, proton is H plus, acceptor. Give me your protons, I'm a base. Now, it turns out water reacting with a proton makes something that's very important, and that's called the hydronium ion. And I will never ask on a test that equation, but I'll use it in a class. When I say hydronium ion, that's H3O plus. This has a charge to it. Now, this shows you a reaction here. HCl is an acid, ammonia is a base, proton transfer, you make a salt. Switch those off for that. You know something? I've done a lot today. We've done a lot today. Let's go back and do one more molarity problem before I let you go, because we're almost done for today. And I forgot to, I'm sorry, it's rare I do this. I forgot to let you watch me write the problem. Now you can see that 6 or 8 points. How many milliliters, that's ml, of a 2.117 capital M sugar solution is needed to get 1.011 moles of sugar. So first, why don't you write here, what are you being asked to find? What are you given? See how nice I am? I let you have some fun too. All right, what are we being asked to find? Milliliters. What are we given? Well, we're trying to find 1.011 or obtain moles of sugar. Who said this was a low-calorie class? Oh, that was bad, sorry. And we're also given this 2.117 capital M sugar solution. And so how do we begin? Well, there's only one number I really have to work with, and that's this. And what units do you want your answer to be? I'm going to make you do all the work. And what units and numbers go on top and bottom of that ratio? Your turn. Let's see if you're up to it. I'm going to, hopefully you are. Wow, you are. So what units are we trying to get to? Well, it's right here, milliliters. And now I'm going to use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to, the units go on top of the ratio. Whatever I'm trying to get rid of, the units go underneath. And I'll write those in. Uh-oh, where do I get these numbers? Well, I come over here and see capital M. That means molarity. And what this really means is 2.117 moles of sugar. Wow, this is a sweet problem. But that was bad. Per 1,000 milliliters. And therefore, this I put in 2.117 moles of sugar per 1,000 milliliters. Notice moles of sugar divided by moles of sugar cancel out because anything divided by a number by itself is the number one. I'm left with milliliters, which is what I want. So I'm going to happily. Whoever said chemistry wasn't fun? It is. I have 1.011 times 1,000 divided by 2.117. And my calculator gives me this number. Are you ready for this? That. Well, how many significant figures should our answer have? And you have the same number of significant figures in your answer as the number with the fewest significant figures. This is 4 significant figures. Remember, 0 after a decimal and in between also 2 non-zero numbers significant. All non-zero numbers are significant. 4 again. And this is an exact number. It's part of the definition, 1,000. So our answer should have 4 significant figures, not 3. I wanted to get out of my rut. 1, 2, 3, 4. Use that number to round off. Is 5 or higher? Yep. So I'm going to drop that. increase that by 1. And I'll get 4.776 times 10 squared milliliters, which would be also 477.6 milliliters. And with that, that's how you do it. I look at the clock. Time flies when you're having fun with milliliters in chemistry and Dr. White. And with that, I'll remember to remind you, don't forget hand-in labs that are due. I didn't have a chance today, but I'll be sending out an email about lab amnesty, so you can hand in labs you didn't and not get 0 points. Don't tell anybody I'm being nice. And, hold on, time out. We're going to go a minute or two late. Sorry about that, but I almost forgot. If we go to assignments, there's the extra credit. And I'll talk about this tomorrow. This is 10 bonus points. And this is an optional project. You don't have to do it, but it's not a group project. Each person has to do their own project alone, or that's called cheating. And I'll do what's in my syllabus for anybody who cheats. Let's just look at this real quick. And the extra credit project is 10 points. It's due by August 1st, the end of the day, 11:55 p.m. or 11:59 p.m. And no late projects will be accepted. For the extra credit project, you have to create a list of ionic and covalent molecules that are found in ingredient lists of products that can be purchased, i.e. means that is things you could use in your daily life. You have to find 5 different molecules that contain ionic bonds and 5 different molecules that contain, this is important, only covalent bonds. The ionic molecules can have ionic and covalent. The covalent can only have covalent bonds. Now, you can only get 3 molecules from a product. To get points, you must hand in a printed table, or in our case, uploaded, with the product name, molecule's name, as is it ionic or covalent. Don't forget to put your name on the table. You'll get 1 point for each correct, a total of 10 points. Now, to make it interesting, you can't use gasoline, water, sodium bicarbonate, carbon dioxide, ethanol, also known as ethyl alcohol, sugar, sodium chloride, oxygen gas, nitrogen gas, or natural gas, which is known as methane. And the example would be Coke. Now, I can use it in my example, but you can't. It has the water as a molecule, and it's covalent. And you can't use sodium chloride, but I can in my example. Campbell's chicken noodle soup, you'll see on the label, sodium chloride, ionic. Ingredients must appear in the ingredients list on a product. You can't say, oh, air has nitrogen. I've never seen an air with, nope, no ingredients. Also, nitrogen gas on do not use list. This is optional. It's not a group project. Now, how do you find if something's ionic or covalent? Well, you look at Google and you can ask your instructor if you need help. And I'll talk more about this tomorrow. Sorry, went over, all 4 minutes. Bad, Dr. White. With that, I'll talk more about the extra credit project tomorrow. And I'll say, Gang gesund. Remember, that's Yiddish, go and help. And in fact, I've known someone at COD who just came down with COVID. Sorry to say, but they did. So be careful, it's still out there. But gang gesund. Goodbye now. I stole that from Beverly Hillbillies Granny. Bye.